Welcome to, I was confused, EE123, lecture 13. Woo! Discrete wavelet transform. Before this, thank you for all that showed up for the demonstration of the, turns out to be partially unsuccessful presentation, because I got this email from Chris Martin, KG7EZ. Just wanted to let you know that you were 5'9", which is, readability is the best. 9 is a really high signal into SO50 satellite. Called you several times, but you never came back. Your downlink, maybe it's the problem with the downlink frequency. I don't think so. It says it was a very active pass, so you should have heard several calls. So I think there's some interference at the UHF frequencies that were preventing it to hear. And maybe that's why I can never get on campus, because maybe there's some source of interference here, so I'll try to figure that out. Once we figure that out, I'll try to do a good demo. But we definitely heard, which is kind of embarrassing, because you're not supposed to talk if you don't hear. But I did it because maybe I thought we would hear something. So I apologize for those who are watching this YouTube video for the rest of the days of the internet. Do you have any questions? Somebody asked somebody something? Somebody asked something? No? Where is the lecture? Okay, so any questions from last time? One of the reasons, by the way, that you're not supposed to call if you don't hear anybody is because of that. It might be a really active pass. You're the deaf person that's like, making lots of noise and ruining it for everybody. Okay, so that's not the good idea. Okay, so last time we talked about an introduction to wavelets, and we talked about the continuous time wavelet transform, and I stopped just about when we were starting to get into the discrete wavelet transform. Okay, so this is where we stopped. So I said that in the early 80s, there's a lot of work in mathematics, coming up with lots of theory of what type of signals and how well coefficients of wavelet, how they behave when you have different type of signals, lots of theorems, math, lots of activity actually in geophysics, because a lot of analysis for geophysics actually uses wavelet type decompositions, especially for oil exploration when you do all these really large studies, when you look at reflections from the ground. These are very useful. Late 80s, people started to link to the work that was in parallel done in the signal processing community using filter banks. And you'll see when we talk about multi-rate signal processing and decimation and upsampling and all these operations, you'll see how those relate to what we're talking about right now. So when you go and you try to map or transform the ideas from continuous wavelet transform into a discrete domain, then there's some subtleties if you want to preserve some of the beautiful properties that these functions have. For example, orthogonality or other type of functions. Okay, one of the functions that or properties that people look at is the number of vanishing moments of a wavelet of the wavelet transform. What does it mean, a vanishing moment? The Haar transform. Okay, the Haar has a zeroth moment. So if you integrate over it, then it will be 0. Okay, so if you know what a moment, the 0th moment is just the integral over the signal. The first moment is t times xt, and then second moment is t squared times xt, integral over that, and so on and so forth. So the number of vanishing moments tells you a lot about the wavelet. So, for example, if the first moment is gone, it means that any signal with a first derivative will basically, if you look at the finest, like if you look then at the wavelet, it will integrate to 0. Okay, so it will not give you any coefficient. It's only the approximation will give you a coefficient. Okay, if something has a second 0th moment, then any second derivative will integrate to 0. Okay? And so in that case, again, any function that has now changes in the second derivative would not have coefficients, only in the approximation, and so on and so forth. So they look at those type of properties, but the question is like how these translate into discrete time. We're not going to go into too much of this. We're actually going to deal with the most simplest wavelet, which is the Haar wavelet, which has just a 0 0th moment. Okay, so its first moment is not 0. Okay. Okay. So when we go from the continuous time into the discrete time, now we can write it in a very similar way as you've written. Instead of sums, instead of integrals, you write it in sums. And we're going to look at two types of coefficients. Okay? The first type are going to be the detailed coefficient corresponding to the mother wavelet. And the second are the approximation coefficient corresponding to the father wavelet, or the plug that we need, the low frequency component that we need in order to plug the representation. So we're going to have this convention. If you look now at the time frequency, the discrete time frequency space, okay, where this is omega, and again, this is all approximate because different wavelets will, they have most of their concentration here, but I mean, like if you look at a square function in time, I mean, it does have high frequencies, right? It does leak, but most of the energy is concentrated. So if you look at the variance, right, it has the same box. So this is kind of a representation or an illustration of what it is. It doesn't mean that a coefficient over here doesn't have some information on the low frequency. It's mostly concentrated over here. Okay. So we're going to have this decomposition where, remember that now the size of the boxes are going to be different for every, for the high frequency, we'd like better resolution in the time domain, but at a trade-off of resolution in the frequency. So our boxes are going to be, more narrow. As we go for lower and lower frequency, we're going to extend our time, uncertainty, and improve the frequency resolution. Okay? The conventions we're going to use are that the detail coefficient in the first decomposition, okay, there's basically levels of decomposition, would be according to a scale, and the second index is position. Okay, so first one is scale, the first one is position. We're going to start with 0. The reason I use this is because with the note that Michael Gaspar used, this is the convention that he used, and I want to follow those. People sometimes use slightly different conventions. So if you look at the time frequency decomposition, so for example, S equals 0, which means a particular a mother wavelet with a certain scale, right? The finest scale would be S equals 0. And then afterward, we're going to stretch it. Okay? So S1 will be a stretch of that, and S2 will be a stretch of that, and S3 will be a stretch of that, and so on and so forth. And U is where it is located in the time space. Okay, so U is that coefficient. So D of S sub U, and then we've also have A of S sub U. So a decomposition is going to look like this. All the D0 something, 0 x and then D1x, and then D2x, and so on and so forth, till we block with some A in here, in this case, approximation, because we put a plug on the scale 2, so it's going to be A2, 0. Okay? So in this case, this would be the finest scale if we have this would be the finest scale, but we could also, stop here. Okay? So if we stop here, then we'll have, two approximate coefficient. Okay, that would plug in the low frequency component. Okay, so here there will be just one coefficient. We did the composition all the way to the end, and so we have one approximation coefficient. And here, if we stop here and we don't decompose further, we don't go for more and more scales, coarser and coarser scales. We're going to stop here, and we're going to have two approximate coefficients. Okay? Any questions? Yeah.
So that means if you closer you go to low frequencies, you get more detail in frequency, number of frequencies.
Well, this is the time frequency space, right? So the highest frequency, you're going to have very good time resolution.
But not as much detail in frequency.
Right, not so much, because it basically splits the frequency. Each one of these coefficients represent, the upper part of the high frequency component. So pi over 2 all the way to pi. Pretty much. It doesn't have, you cannot distinguish between, two frequencies beyond pi over 2 and pi. Okay, with coefficient. There's just uncertainty there. Okay, so if I give you a signal which has that kind of frequency, that's slightly, let's say 3/4 of a pi and 3/4 of a pi plus some epsilon, I won't be able to distinguish between them. Okay, not in the frequency. Like there's frequency uncertainty there, right? But if something changed from this time point to this time point, I will be able to have that time resolution. Okay, as I go for this part represents 0 to all this part represents 0 to pi over 2. Okay, so the detail coefficient is pi over 4 to pi over 2, and the approximation coefficient in this case is 0 to pi over 4. Okay. And there's a reason why they call them approximation coefficient. You'll see. You'll see why it means approximation. Yes?
So does that mean that for highest frequency coefficients for the wavelet transform will always have it be from pi over 2 to pi, or you can have a wavelet transform that has better resolution than that?
Well, you could decompose this further at the expense of losing temporal resolution. Right? It's always this trade-off. But with the classic wavelet decomposition, where we split all the time like this, then yes. But you can have other decomposition that we have other splits. And you'll see how you can actually do this when we get to actually how to compute it. Yes?
So in this case, we have 2 plus.
What do you mean by 2 plus?
Like we got A10 and A11. Like A represents the factor of other wavelet.
Yes.
Okay, wait.
So they will have two functions, basically a translation of these functions, right? 2 translations of the father wavelet, yeah. It's not just going to be one. And you'll see what does it mean, actually. So here's an example. Let's look at the discrete higher wavelet for n equal 2. Let's say we have a signal n equal 2. The mother wavelet looks like this. The father wavelet, or the scaling function, or the approximation, okay, looks like this. Okay, so this is the best. I mean, this is phi 0, 0, and phi 0 and psi 0, 0, and phi 0, 0. And the reason that it's only 0, 0 is because our signal is 2, right? Size 2. Okay, so we can only decompose it once. That's it, done. Okay, In that case, if I multiply with this function, basically, okay, I do an inner product with this function. So the first coefficient that I have, I multiply with this. The second coefficient, I multiply with this, and then sum them together. And then this one, I multiply with this, and then sum together. This will give me a decomposition that looks like this. I have a detail coefficient and I have an approximation coefficient. Turns out, equivalent to DFT2. Exactly. To a normalized version of DFT2. Okay, normalized by square root of 2. But it's exactly like DFT2. You add, subtract. Okay, add two numbers, subtract two numbers. Low frequency, high frequency. I mean, this is exactly what DFT2 would do. It would try to separate into a high frequency component and low frequency component. Okay? So that kind of makes sense. Right? Makes sense. Okay. So now the question is, what would that look like for har n equals 8? And for some reason, this doesn't look right. Okay. Oh, no, I think it's fine. Is that right? Yeah. Okay. Let me back off a little bit. There you go. Okay. Yeah, these shouldn't have been here. So if we look for har equal 8, then psi 0, 0 would be the har kernel located at one side of the signal. Okay? I mean, these are basically basis functions, right? These are basis functions. We're going to represent by coefficients of basis functions. Basis function of Fourier's would be, of a DFT8 would be some complex exponential series with some linear phase across, this, of 8 numbers. Now, it doesn't look like this anymore. Now, psi 0, 0 would basically be this basis function. What does it represent? It represents a high-frequency component because it looks at the derivative or the difference between 2 points at this position. So it has high-frequency component information that is corresponding to a particular position. Where would that correspond to the time-frequency space? Who wants to be the brave soul that says it? From this side? Top left, that's right. This. So if I look at the inner product of my signal with this function, I'm going to get a coefficient value. That value is going to represent the frequency information, high frequency information, at this part of time. So what would be the second one? And now I'm talking about orthogonal har wavelet, discrete orthogonal har wavelets. So orthogonal means that they don't overlap. So now it's a function that looks like this, okay, where it represents high frequency at around this position, okay, corresponding to this one. Now here is high frequency at this position, corresponding to this one. And then this one corresponds to this one. Okay? So now this is the first scale that I'm going to be computing. Okay? So after doing an inner product, so multiply and add with this function, then multiply and add with a second one, multiply and add, I'll have information about high frequency components at 4 positions in time. Okay, so I have time and frequency information, right? But I don't have very good resolution in the frequency, right? It's pretty coarse. It represents mostly information from pi over 2 to pi, right? If I needed more resolution and frequency, I will need more support. That would reduce my resolution in time. But the highest frequency, we don't care so much about the frequency resolution as much as we care about the time resolution. Okay? So what will be then the second scale? So phi1 0 and phi 1, 1 would look like this. They're basically stretched. Obviously, they're orthogonal to these guys, because whenever this one overlaps with this one, this has a plus and negative, plus and minus. So if you multiply this phi 0, 0 with phi 1, 0, if you multiply them, then you'll have a minus 1 and a 1, so those would cancel. And then this overlaps with 0. So if you multiply and add them, there'll be a 0 inner product between them. Okay? And obviously, this one is orthogonal with this one because, again, they don't have overlap. Now, this represents kind of a bandpass filter now. Look at this. It looks like a bandpass filter. Okay? So represent some bandpass information at the position of the first half of the signal. And this is a bandpass information representing the second half of the signal, corresponding to da-da-da-da, da-da-da-da. Right? That's pretty awesome. Now, if I did overlap, so if I didn't do an orthogonal decomposition, so I would have somewhere in between, which will be -1, -1, 1, 1. That will be in between. Where would that be in the time frequency space? Halfway between, that's right. It will be here. But it will have that kind of uncertainty. It's the same thing as the zero padding, and it's the same thing as the R and the time frequency. If we overlapped windows, we still have the uncertainty, but it will be just centered around another point. Okay? So now I can go for another scale, so psi 2x. And in that case, when I have a signal size 8, there's just one coefficient left. Okay? And that coefficient looks like this. So it represents a bandpass centered around the middle of the signal. Voila. There you go. Bandpass centered around the middle. And then I need to close the gap and do a approximation coefficient, which in this case would be just a constant. And why is it an approximation? Because it's the DC component. I mean, if you want to represent something, any signal, by one coefficient, I would say take the average. Right? So that's why it's approximation. Any questions? This is hard to digest. Yeah.
Can you explain why orthogonality is important?
Why orthogonality? Well, it depends. Orthogonality is nice because energy in one domain is exactly the same in another domain. There's a beautiful inverse between those. There's no loss of information between one or the other at a cost. For example, in this case, I lost my translation invariance. If I have a signal that I'm going to put this into this transform, if it's shifted by one sample, I will not get the shifted version of the wavelet transform. Okay? So that will be a cost of orthogonality. And orthogonal wavelets are good for some things. Reconstruction is super easy. But also non-orthogonal may have some nice properties as well. Okay? But there's something nice about orthogonality. That's why DFT is orthogonal. It works great. There's beautiful properties for orthogonality. Noise propagates nicely. There's actually an inverse. If it wasn't orthogonal, there isn't really an inverse. There's what's called a pseudo-inverse that goes from one to the other. For example, for the case of the overlapped window in the short-time Fourier transform, if I made any changes in the short-time Fourier transform, they might not be a signal that if I took the forward for short-time Fourier transform will map to the exact values. Because it's not just inconsistent. So I need to find the closest solution that will do that. So it's a little bit more complicated. Because I'm mapping a n-dimensional space into a larger dimensional space when I'm talking about if I did overlap, then I would have more coefficients end up. If I start with 8, I will end up with 16 maybe or more. So now you have a higher dimensional space. So something lower dimensional proportionality, you map to a high-dimensional space. If you want to go back, you have to project it onto that space. Okay. Does this make sense? Yep.
Yeah, I'm still a little confused with the father function. Why do we add that in?
Well, we want to stop the decomposition at some point. Okay, so we need to plug it in with a low frequency component because we cannot keep on dividing. At some point, we just don't. I cannot represent all the signals with just 1 minus 1 or stretch version of it. I need to, at the end, compute the mean because I'm losing that coefficient. So that's what the father wavelet is for. And if I want to stop my decomposition at this level, and so I want to just break it into something like this, then I need to do a low pass. I need to have a low pass information. So I need something that has a low pass information.
Are these a basis?
Yeah, these are basis functions. This is a basis function. It's orthogonal basis. They're norm 1, orthogonal to each other. Yeah, this is exactly. It is a basis. It's an orthonormal basis. It's much more powerful than just a regular basis. Okay, let's see how you can actually compute this. And not only compute this, but compute this extremely fast. What was the complexity of the DFT? O of n log n, right? I'm going to show you that we can actually compute it much faster. Okay. All right. Okay, so now we have H0 and H1, which H1 is the corresponding to the mother wavelet or the detailed coefficient, and H0 would correspond to the approximation. Okay, so what I could do, if you think about this, I mean, it looked like. Before, if you look, it was kind of shifted version of, like you multiply and add with shifted versions of this kernel, right? Before. So what I'm going to do is I'm going to perform this as a filtering operation. I'm going to convolve x of n with h1 of n, h0 of n, which will give me the approximation coefficients. And I'm going to convolve x of n with h1 of n, which will going to give me the detail coefficients. Is that right? And that would supposed to give me this, right? I'm doing a high pass and a low pass. Is that right? If I do that, how many coefficients I'm going to end up with? I'm going to end up with too many coefficients because I'm looking at all possible translations, right? So if I have an 8-side signal, convolving with here will give me something, well, 8 is, let's go to, like, if I have a 1,000,000-side signal, I'm going to end up with approximately 1,000,000 high detailed coefficient, approximately. And then if I look at the approximation coefficient, I will also end up with approximately 1,000,000. So now it's 2,000,000 approximately. So it's not good. We wanted to preserve orthogonality, right? And so what we are missing is, so basically this will give us a decomposition which is broken into half and then overlapped. So we have these overlapping between. So what we need to do is we need to downsample. So what we're going to do is we're going to convolve with a low pass, downsample, convolve with a high pass, and downsample. And that is exactly, this operation is exactly equivalent to performing these inner products that I showed before, with a basis function that I showed before. So low pass, high pass. And it kind of makes sense, because low pass will give me the approximation coefficient. High pass will give me a detail coefficient. And because it's a convolution, it's going to be shifted in time. So I'm going to see, those high frequency component shifted in time. So this will give me that kind of a decomposition. Now I want to get the second level. So what do I do? What do I do? Well, if I just downsample, I mean, that would not separate anything. I'll get aliasing. Convolve again with the approximation coefficient, with the low pass and the high pass, and then downsample again. That would then decompose the approximation into its high frequency component and a low frequency component. And then I can keep on going and do this to the approximation. And again, and again. So every time I'm just going to take the approximation coefficient, I'm going to pass them into a high pass and a low pass, and then downsample. Take the approximation, high pass, low pass, and then downsample. So this part over here will give me A0 and N and D0 of N. And if I decide to end, then I have D0 and I'll have A0. But if I decide to keep on going, if I want to get D1, then I need to take A0 and convolve it with H1, and I'll get the D1 coefficients. If I want to get A1s, I'm going to convolve it with H0. If then I want to get D2, I will convolve this with H1 to get D2. This, the next level, and the next level, and the next level. And every time I'm going to break this into half and half and half, and eventually put a plug with an approximation. Okay? So what is the complexity? N over 2, N over 4, N over 8, N over 16. You sum all of them, N. It will maximally go to 2N. Okay? So it's order of N. That's pretty sweet. I can do really fast computation using this. Okay? And the reason I can do this is because I decimate. If I don't decimate, that's a problem. I get more, well, it depends. If I don't decimate at all, then that's a problem. Sometimes you don't want to decimate, but then decimate afterwards. Or like decimate just this and keep those. But depends. Okay, so a decomposition, a wavelet decomposition would be like this. Now the question is, given coefficients, how do I do a reconstruction? You know what's beautiful about this? Is that I can have reconstruction filters that look like a flipped version of the decomposition filters, so G0 and G1. And they have this particular case has a property of a perfect reconstructing filters. And we'll get to that when we talk about the multi-rate. I'm not going to go over it right now. But all you need to do is flip the arrows and replace H's with G's. So now you've got A1 and D0, you upsample, and then filter and then add. And then you've got the D0 here, then and A0 that you got from here, then you upsample, convolve with G0, convolve with G1, and then add, and so on and so forth. So again, the reconstruction is very simple. Okay? Requires now an convolution and upsampling. Upsampling and then convolution. The other case, the decomposition requires convolution and then downsampling. Okay? Let's see an example. Okay? Here I start with a signal that looks like this. Why did I pick this kind of a signal? It's piecewise constant, and it's perfect for a hard type decomposition, just because of the shape of those basis functions. So when I take this, I'm going to compose detail coefficient and approximation coefficient, which are D0n and A0 of n. Okay? N means where I am on the time axis. Okay? So when I do that, I get some detail coefficient for the first step, and you see that the detail coefficient always appear at some discontinuity. Now, the reason you don't see a detail coefficient over here is because there was one, but I downsampled and I lost it. So if I didn't downsample, you would see something here. But because I downsampled, I lost it. It's not that I lost the information, because that would be redundant. Okay? It's a redundant information because eventually I'm going to have it at a different scale. Okay? So this is the detail coefficient. And look, this is why this is called approximation. Coefficients. Do you see why? Because it approximates this. It's a downsampled version. Now, if I did a low pass and then downsampled, it would not look as nice as this. So this is a better approximation for this particular class of signals than I would do with the low pass. Like we will learn later, when we talk about downsampling, we would see that we have to low pass filter and then downsample. This is a better approach for this class of signals. Okay, now we're going to take this approximation coefficients and we're going to perform, again, detail and approximation on them. So I took that, and now that's the detail coefficient. And again, they always are at an edge. Okay? That's why they're details. Details in a signal is really the changes. So whenever there's a change, we're going to see detail coefficients. Okay? And then why is it called approximation? Okay? So it's and you see it's sparser, right? It's only 64 coefficients, right? 64 and 64, and then I had the other two, right? So eventually it leads to... So 64, 64, and this. Yeah. Anyway. Go on. Detail 2, A2. Again, this is an approximation of the original one. Okay? But now it shows details of that scale. So again, changes here, changes here, changes here. And another one. And another one. And now I'm going to stop. That's the last one. And you see that the approximation coefficients are just, 18 and whatever, 10, something. Right? But if you look at the signal here, if you want to represent using two coefficients, I would say, take something, an average over here, and take an average over this one, which is like a high and a lower value. A high and a lower value. Okay? That's a... If I want to approximate this with two coefficients, I would get something like this. Okay? And again, all the details appear over here. Now I can show you in a different way. So these are the scales, and ignore this because that's what ImageSC was displaying, but I didn't have time to erase it. But these are the right scales. 0, 1, 2, 3, 4. And these are the positions. Okay, ignore those numbers because they're only true for the signal itself, but afterwards I decimate. So that's why they're kind of like getting blockier and blockier. Okay? And these are undecimated. So I didn't do the downsampling operation. I kept them so you could see the details appear. And this is very similar to the continuous wavelet transform that we had before, right? When we had the signal and you saw those bumps showing up along. And so you see that you have an edge, and the edge kind of spreads its information. And you have an edge here, and it's like spreading it. An edge, and I kind of look at it at different scales of change. And at the end, I'm ending with an approximation coefficients, which approximate the intensity of the signal. If I did a decimation, it's going to look like this. That's after decimation. Okay, so it does represent still very nicely the edges at different scales and the approximation. Any questions? Yeah.
The square in the middle of that image, is that like?
That appears, I guess, in this position at this kind of scale of frequency. So there is kind of change that happens here at a kind of zoom out scale. It probably, right. So it sees that, I guess, the whole thing here. Yeah. It captured this whole block, I guess, of change. Yeah. These coefficients representing, they also have a negative sign. So negative and positive, it's not just magnitude. Yeah. Black is negative, black is the negativist negative. and white is the most positive. I should probably draw on a color bar for you to see.
It's not describing the magnitude, and what does the coefficients describe? What does it tell us?
Well, their magnitude tells you how much of an edge, but it could be negative or positive. It's kind of phase, but it's real. So it's real. It's like positive and negative, right? Yeah, so it is kind of a phase. So another way to display this is another way where I just draw it as a vector, where these correspond to D0n, this is D1n, this is D2n, and A2n, and so on and so forth. It doesn't show nicely the correspondence between the edges, though. Okay, but it's another way. This is just plotting an array, just an array. Okay, so I take this and I get that, and I can take that and do an inverse and then get back to this. But here's what's interesting about this. Look. The signal here had information almost in every point, and for every n had some value. What happens after I did a Hard wavelet decomposition? It became sparse. It's the broom. The broom that makes piles of signal, piles them into sparse number of piles. Just takes a signal though. Okay? It's beautiful. What does this allow us to? Compression. Yes, there's only 26 coefficients that are non-zero here. I can take a 256 signal and represent it using just 226 coefficients exactly. How many bits do I need for this? I need to store the coefficients, right? I also need to store their position. Okay? So there's a log n cost in that. So 26, some log n order of, right? So I can compress it by almost a factor of 10. Okay? Probably like a factor of 7. Something like this. Just by performing a wavelet transform and then storing just the non-zero coefficients. Think about it. This is compression. Actually, Wavelet 2000, it's JPEG 2000, which was it's an image compression standard, uses wavelet transform for compression. So I could also, for example, just store the largest 20 coefficients and hope that it would represent better or approximate my signal better than any other type of coefficients. And here's an example. If I reconstructed using 25 coefficients, of Hard coefficients, I get a perfect reconstruction of my signal. Okay? If I actually computed a DFT and took the largest 25 components, this is what I get. So DFT is not very good in representing signals that are piecewise constant, sparsely. Because any edge would spread out in the frequency domain. The beauty about the Hard decomposition, it doesn't. Okay, so it allows me to do that. The other thing it allows me is, what if my signal was noisy? There's a case where my signal is noisy. How does noise translate into coefficients in the Hard? This is orthogonal transformation. Orthogonal means that any random variable, like any, let's say this is Gaussian distribution that's IID, independent distributed, it would also translate into an IID Gaussian in the Hard transform. So the distribution of noise doesn't change because it's orthogonal. Okay? But the signal is put into piles. So now we just need to wipe out the empty spaces in between. And if we threshold, put a threshold here, and or just take the largest 25 coefficients, okay, then this is what I get. This is beautiful denoising, right? It's really close to this. Whenever it's flat, it's flat. I mean, there is some noise because I didn't throw away, there is noise that contaminates my coefficients, but it's much smaller. Okay? So you can get beautiful denoising that's adaptive just because you're putting these thresholds that adapts to your signal. If I try to do that with a low-pass filter, there's just no way you would be able to do this. Okay? You would have to make like some adaptive, assume that you'd only do an averaging whenever it's kind of flat, and whenever there's a change, you don't do any averaging, and it's really complex to do this. Here, you just do a wavelet transform, threshold, inverse wavelet transform, done. Beautiful. Sparsity, so powerful, so powerful. I mentioned that you can do it with compression. So here's a picture using a photo booth. This is a JPEG 2000 wavelet compressed. This is JPEG compressed. JPEG uses the DCT, which is a block DCT, so it takes blocks of 8 by 8, and then computes a DCT, which is something similar to the DFT, but not really, just using a cosine instead of a cosine plus I sine, and then performs some quantization on those coefficients, and then stores them. Okay? Wavelet does that on takes bigger blocks, computes the wavelet transform, and then does some quantization of the wavelet coefficient, and then stores them in a particular way. So this I'm showing you is a 66 time fold compression ratio, which is pretty good. You can't really see the differences. They all look pretty good, right? But if you zoom in, you start seeing the effect of overcompression in JPEG, because you kind of see, because it's based on blocks by blocks, you would see these blocky artifacts. And because wavelets don't actually, this is actually a two-dimensional wavelet. I didn't talk about how a two-dimensional wavelet looks like, but you can see the time-frequency decomposition again in over 2 dimensions. Okay? But it does preserve all these nice edges in the images. Whenever it's smooth, it smooths out nicely, and it really is a better representation of the original signal. Okay? So if you're going to push your compression ratio quite a bit, then you should use wavelet 2000 as opposed to wavelet. Here's another example. This is a brain image, and it's quite noisy. I'm going to do a two-dimensional wavelet decomposition of it. It looks like this. These are the coefficients of the two-dimensional wavelet. Now, the thing is, when I do a high-pass, low-pass, high-pass, low-pass, now I have 2 dimensions to do them. Okay? So this would be D0x, this 0xy, and this is D0y. Okay, so I take a derivative or a high pass in the x direction. Here I take a high pass in the y direction. Here I take a high pass in both. And so you only see the edges, really, of the detailed coefficients. Then I take the low pass component, and I decompose it again. And then I take that, and I decompose it again, and I get an approximation coefficient over here. Okay? So I hope you can kind of see how that translates to. But look what's beautiful about this. I took a brain image which has information everywhere, but now it becomes sparse. So now what I could do is threshold this and then reconstruct. And those will be the differences. Okay? So you get much better denoising. Actually, this I did hard thresholding, and that's why you still get some annoying stuff. But there's ways to actually get even better, but I didn't want to confuse you even more. You do a soft thresholding, but some other time. Some other time, some other place. Yes, quickly.
Just wondering about the previous slide.
Yep.
What would the Gaussian and not Gaussian? What would the probability distributions look like?
It's still Gaussian.
Still Gaussian.
Yep. So it's orthogonal. It's orthogonal transformation. It's still Gaussian. Okay, so here's for compression. Let's say now I'm going to reconstruct images from wavelet coefficients, and I'm going to add more and more and reconstruct images. This is from like one coefficient. I'm going to add more and more coefficients. Look how the image starts to improve. And it's kind of like a low resolution to high, right? coarse to fine. That's the beauty about those scales. So as I get to about 5% of the coefficient, it's almost perfect. Okay? So as I add more and more, I get more approximation. Here's another example. This is Lena, very famous. This is decomposition, again, makes it sparse. For the last 2 minutes, I'm just going to say something about something that's more related to research. It's a paper by where he uses those ideas of multi-scale decomposition in order to denoise flow fields. So now it's not just one dimension, it's really a vector field that you can also compute these flow fields on. And this is flow fields in MRI, this is blood flow in the heart. You can get that signal from MRI, and you can see those flow fields in the heart. And the problem is that they don't obey really because of noise, they don't obey the laws of physics. In MRI, in general, blood is non-compressible, so whatever flows in has to flow out. And obviously, when you have noise in the field, it doesn't obey this. So we were looking at ways to denoise that by imposing on the reconstruction that the flow needs to have zero divergence. Whatever flows in has to flow out. So we use these wavelets that has the property of always representing divergence-free or non-divergence-free components. And this is just by choosing those wavelets. And after you do this decomposition and you do the denoising, this is what you get. Okay, so a much better approximation. Whatever flows the right way, as opposed to here where it's going to be really, really noisy. Okay. So with that, I conclude today, and I will see you on Friday when we start talking about sampling, my favorite topic.